A variation on the direct comparison test is the limit comparison test. This is pretty similar to the direct comparison test in terms of the fact that you will take a series that you're interested in studying and compare it to a similar but easier to understand series. But instead of checking whether the terms, the AN terms, are always less than or are always greater than the terms of the series you're comparing to, instead you'll take the limit as n goes to infinity of the quotient of the terms of the two series and see what result you get. And under the right circumstances, that will tell you that the two series, the one you're interested in and the one you're comparing to, both have the same behavior. Here's our theorem. Suppose that the sum of AN and the sum of BN are series with positive terms. If the limit as n goes to infinity of AN over BN equals C, some number C, where C is a finite number that is greater than 0, then either both series converge or both series diverge. Note, this does not work if your limit ends up being infinity, or if your limit ends up being 0, then you cannot draw this conclusion. Let's see some examples. Let's look at the series, the sum as n goes from 1 to infinity, of e to the power of n plus 1 plus 3, all over 2 to the n plus e. Let's see whether this series converges or diverges. This would be a tricky one to try and use the direct comparison test for, because it'll turn out that this series is not easy to find out whether it's greater than or less than the terms of similar series that you might want to compare to. It'll be difficult to make that kind of comparison directly. But the limit comparison test gives us a little more flexibility about what series we can compare to. Let's start by taking our AN terms here. And they are e to the power of n plus 1 plus 3 over 2 to the n plus e. Now, a good thing to do here is to look at the function that describes your ANs. Often it will be a quotient. If it's not a quotient, there's a good chance that it's not going to satisfy the test for divergence anyway, so you're usually going to have a quotient. And on the top and bottom, you'll probably have some components of it that are growing faster than others. In this case, I see that I've got an exponential part, e to the n plus 1, plus 3. So maybe I'll just sort of imagine that I cross out that 3. And on the bottom, I've got 2 to the n plus e. This is similar to e to the n plus 1, but actually I'd like to say that's e to the n times e over 2 to the n. It's not exactly the same. It's not equal to it. It's tricky to determine whether this actual terms of the series are greater than or less than what I've just written down. So the direct comparison test would be rather tricky to use. But we can use this. In fact, if you have e to the n times d over 2 to the n, you could compare this to a geometric series. In fact, let's take an even simpler geometric series. Let's let our bn's just be e to the n over 2 to the n, which is the same thing, of course, as e over 2, all to the power of n. So this is a good series to compare our series to. Let's try it. Let's take the limit as n goes to infinity of an over bn. So the nth term of our series divided by the nth term of the series that we're comparing to. That is going to be the limit as n goes to infinity of e times e to the n, easy just to work that out right now, plus 3. We can't drop off the 3 there. We need to see what happens in the limit, divided by 2 to the n plus e. That's our an. Now we're going to divide by e to the n over 2 to the n. And now we just have the work of simplifying this expression and getting this into a form we can actually work with. So this equals the limit as n goes to infinity of, okay, now I've got a fraction divided by a fraction. What should I do with that? Well, the very first thing I should do is convert that to multiplication. We've got times e to the n plus 3 over 2 to the n plus e times the reciprocal of the fraction we're dividing by. So that's going to be 2 to the n over e to the n. Now, what I'll do now is a little bit of rearranging here. This is equal to the limit as n goes to infinity of, let's see, I want to group the parts that have the e to the n together and the parts that have the 2 to the n together. I can rearrange this any way I want to because we're just multiplying two fractions. The result is the product of the two numerators divided by the product of the two denominators. So I can say e to the n, my e times e to the n plus 3 over e to the n times 2 to the n over 2 to the n plus e. Now at this point, we're experienced enough at limits to be able to do this without too much difficulty here. What we could do, if we want to do this very explicitly, is take that first fraction and we'll divide the top and bottom by e to the n. And that's going to give us the limit as n goes to infinity of, okay, that first part's going to be just e plus 3 over e to the n over 1 times the next part. What's the next part? Well, for the next part, let's actually divide the top and bottom by 2 to the n. And we'll end up with a 1 on top and a 1 plus e over 2 to the n on bottom. Let's make a little more room here. So, now that we have some room, let's just finish evaluating this here. This first part is now a number, e, plus, well, 3 over e to the n. As n goes to infinity, this part's going to go to 0. So just e over 1 times, well, we just have 1 over 1 plus e over 2 to the n. Now, e is just a number. So a number over 2 to the n, as n goes to infinity, that part's also going to go to 0. So we have times 1. This limit is equal to e. Now, what does that tell us? We have to kind of rein our minds back to focusing on the problem at hand. We've just computed this limit, the quotient of the terms of two different series that we're interested in. And we got e. Now, the important thing here is that e is a number, and specifically a number that is not 0. So we didn't get infinity for our limit, we didn't get 0 for our limit, we got a number that was greater than 0. That tells us that either both series converge or both series diverge. So the question is, does the sum of e over 2 to the n converge or diverge? Well, that's a geometric series. And our r is equal to e over 2. So how big is that? Well, e is about 2.718 over 2. So this is definitely greater than 1. So if we have a geometric series with our r being greater than 1, then our series diverges. So what this tells us is that our original series also diverges. And there's our answer. Let's look at one more example. the sum as n goes from 1 to infinity of the square root of 6n to the 5th minus 2n, all of that over 2n to the 3rd plus 7. This is another really tricky one. We can't really use the direct comparison test here because it's going to be really difficult to figure out exactly what to compare it to and whether it's greater than or less than whatever we're comparing to. The limit comparison test is more flexible because we don't have to prove that our terms are actually strictly greater than something else or strictly less than something else. As long as the quotient of the two terms from the two series approaches some constant, some value that is not 0, then we're good to go. So the question is, what series should we compare this to? Now, a good rule of thumb here is to do the same kind of process that we just did in the last example. Let's take our ANs, and this is equal to the square root of 6n to the 5th minus 2n, all under that square root, all divided by 2n cubed plus 7. And let's just start tweaking this a little bit and modifying it, and just try and see if we can sort of chop off some parts we don't like and turn it into a much, much simpler function. In fact, what I'm looking at here, what I'm seeing here is that the function that describes my ANs is an algebraic function. It is built out of powers of n and constant multiples and sums and differences and products and quotients and roots. So if your function is built entirely out of constant powers, constants, powers of n, addition, subtraction, multiplication, division, and roots, and nothing else, and you don't have any variables in the exponent, or any trig functions, or any logs, or any of those things, then you've got an algebraic function. And in general, algebraic functions showing up in a series, it's a good indication that the limit comparison test using a p-series for the comparison is going to work for you. So let's do that. Let's start by just sort of lopping off some of the slower growing portions of this expression and see what we get. So I got 6n to the 5th. If I subtract 2n from that, that's not going to grow as fast as n goes to infinity. So the 6n to the 5th is more important. Now, that square root is still important. And on the bottom, that plus 7 is not that important, but the 2n cubed is important. Now, what I'm about to write is not equal to an, but let's say it's approximately equal to an. It ought to give us a good series that we'll be able to compare to the one we have here. So let's look at the square root of 6n to the 5th over 2n cubed. So the square root of 6n to the 5th, well, let's see. The square root of 6, I'll just write as the square root of 6. That's a constant. I don't really care, to write it as a decimal. That's an exact term right there. Now, n to the 5th power and then taking the square root of that means we actually have n to the 5th power and then to the 1/2 power. That is n to the 5/2 power. And we are dividing by 2n cubed. Now, those constants, let's just pull out here. We've got root 6 over 2. That could be simplified a little bit, but it's hardly worth it. And n to the 5/2 divided by n cubed, that means you can subtract the powers. And if the power is higher on the bottom, you'll end up with something on the bottom. If the power is higher on the top, you'll have something on the top. So 5/2 is 2.5. It's 1/2 less than 3. So this is times 1 over n to the 1/2 power. So what series should we compare to? When you're doing the direct comparison test, you will sometimes need a multiple of a known series, a constant multiple of a p-series, a constant multiple of a geometric series. If you're doing the limit comparison test, that constant multiple will take care of itself. All it will affect is what non-zero number you get in your limit if you are choosing an appropriate function to compare to. So I'm going to just totally ignore that root 6 over 2, and I'm going to let my bn be 1 over n to the 1/2 power. Now, we think this is going to be a useful series to compare to. The series, sum as n goes from 1 to infinity, of 1 over n to the 1/2 power. We suspect that this series will be comparable to the series we're starting with, and that when we take the limit of the a_n's over b_n's, that we'll probably get a constant. In fact, I think we're going to get a constant that's related to that constant I crossed out earlier. So let's just do the last part of the question now. Does this series converge or diverge? Well, this is a p-series, and our p is equal to 1/2. Remember, the p is the power on the n on the bottom. So technically, this whole 1 over n to the 1/2 is the same thing as n to the negative 1/2. But your p is positive 1/2 by convention. That's just how we define p-series. And we know that when the p is less than or equal to 1, then our p-series diverges. Now, are we done? No, we're not. We're not done because we haven't yet done the limit comparison. We haven't yet confirmed that our series and the one that we just wrote down actually have the same behavior. So we need to do that. So let's make a little more space and let's actually do that. So let's find the limit as n goes to infinity of an over bn. And that is the limit as n goes to infinity of the square root of 6n to the 5th minus 2n over 2n cubed plus 7. All of that divided by our bn. But I want to save myself a step here. If I'm going to divide by 1 over n to the 1/2, it's the same thing as multiplying by n to the 1/2 over 1. And actually, n to the 1/2 is the same thing as the square root of n. So let's write that way. So, what can I do? Well, now it's a question of using algebra. If you have chosen the p-series appropriately that will be comparable to your algebraic function, then it should be possible to do some algebra to manipulate this thing until you can actually solve the limit. Really, at this point, it's using all the skills that you've already learned for solving limits of algebraic functions as n goes to infinity. And usually what that's going to mean is doing some algebra up until the point where you can afford to divide the top and bottom by the same power of n. And if you do that right, you should end up with some expression that actually does not give you an indeterminate form. So let's try that. Let's do some algebra here and make this work. So the limit as n goes to infinity of, okay, first things first. I have a square root times a square root on the top. That means I can multiply the expressions that are under the square root. So we have the square root of 6 n to the 5th times n is n to the 6th power minus 2n squared. All I did was multiply that 6n to the 5th minus 2n times the n, because both of those expressions are under the square root. And we are still dividing by 2n cubed plus 7. Okay. Now, if you try to plug infinity in for n right now, you're going to find the top is going to infinity, the bottom's also going to infinity. That's an indeterminate form. You do have the option then of using L'Hopital's rule here, but L'Hopital's rule is not always the best choice when you have an algebraic function, because it's going to reduce the powers on these things, but it's not actually going to allow you to simplify much right now, and you'll probably have to use L'Hopital's rule multiple times. It'll just be a huge pain. Nobody wants to do that. Instead, let's do some clever algebra. I want to divide the top and bottom by the same thing. I want to divide the top and bottom by a power of n. In particular, I'm looking at this denominator here, and I'm seeing, well, I've got 2n cubed plus 7. Now, the 7 does not grow as fast as the 2n cubed. I think if I divide the bottom by n cubed, I will be able to get an expression that does not have infinity in the end. I'll have the bottom will be then approaching some number. But I also have to divide the top by n cubed. But here's the trick. Because the top has a square root, I'm actually going to divide by a square root. Now, what square root can I do? Well, the square root of n to the 6th is n cubed. So by doing this, by dividing the top by the square root of n to the 6th and the bottom by n cubed, I'm actually dividing the top and the bottom by the same thing. And now let's see what we get. So we end up with the limit as n goes to infinity of, all right, let's see now. Again, on the top, I have an expression under a root divided by an expression under the same root. So because we are dividing a square root by a square root, we can divide the things that are under the square roots. So 6n to the 6th divided by n to the 6th is 6. And minus 2n squared over n to the 6th, that's going to be 2 over n to the 4th. All still under the square root. And on the bottom, I'm dividing 2n to the 3rd plus 7 by n to the 3rd. That's going to give us 2 plus 7 over n cubed. And now, I'm actually ready to plug infinity in, because 2 over n to the 4th, that's going to go to 0 as n goes to infinity. And 7 over n cubed is also going to go to 0 as n goes to infinity. So now we're actually ready to go. We're going to put the square root of 6 over 2. I told you we would end up with a constant that was the same as the constant that I crossed out when trying to decide what to use for bn. That constant takes care of itself. You did not have to introduce that root 6 over 2 into your bn series that you're comparing to, because it'll just take care of itself. We end up with this constant here. So again, the important thing here is we got a constant, a finite result that is greater than 0. That tells us that both series converge or both series diverge. And we've already figured out that our bn series, the sum as n goes from 1 to infinity of 1 over n to the 1/2 power, that's a p-series, with the p being less than or equal to 1, and that series therefore diverges. The series that we compared to diverges. Therefore, the series that we're interested in, the series that we were looking at in the first place, also diverges. And we're done.